g is 16, right? G is this is the g. So we'll use the method of Lagrange multipliers. We'll take the gradient of f, which is y e to the xy, x e to the xy equals lambda times 3x squared, comma 3y squared. I can solve both of these for lambda. I think that's the easiest thing to do. So lambda gives me y e to the xy over 3x squared equals x e to the xy over 3ay squared. Hooray, the e to the xy's cancel. Yay. And that gives me this over that equals that over that, which gives me that y cubed equal to x cubed. Hey, that's not too bad, because then I can go back up here. And that gives me 2x cubed equal to 16. So I can get x is equal to the cube root of 8, which is 2. All right. Then let's see here, y cubed equal to 8. So that's got y equals to 2 as a solution, the real solution. And there are two other solutions. But anyway, so f of 2, 2 is e to the 4. This is the global maximum. And so, but it's not, I mean, this curve is not compact, right? So the method of Lagrange multipliers actually finds for us a maximum, but not a minimum. Now, how do I know it's the maximum? It requires further analysis, really. So 2, 2 is this point right here, and it's the maximum because you can think about this, right? If you think about the values of x, y, what happens to x, y as you go off this way or that way? Right, they become negative, so you're looking at e to the minus something, right, which is like less than 1. On the other hand, that point right there is e to the 2 times 2, which is e to the 4. That's the largest it gets. And then this thing asymptotically goes to 0 along both of the tails. So it's global. It is bounded below globally by 0, right? Because it's an exponential function. We know 0 is below the exponential values, right? But it doesn't attain 0 because 0, you'd have to go to the point at infinity to actually get to 0, right? So unless you're, I don't know, I guess you have to go to like the train man or whatever to get there. But let's see here. Is it the train man? I don't know, I watched it a couple weeks ago. I've forgotten already. So this movie's so forgettable. You guys don't remember. You know when Neo ends up at the train station, didn't know how he got there? I feel like that's kind of like the point at infinity. It's outside the matrix. It's sorry. Too obscure a reference. I'm sorry. Let's see here. So if we want to find the extreme values of x, y, z on this ellipsoid, again, take the gradient of f equal to lambda times the gradient of g. You got these three equations. And have you ever solved equations like this before? Probably not, right? So you got new algebra to learn here. And let common sense be your guide. If you divide by something, you better be sure it's not 0, because if it is 0, that's a separate case. So divide and conquer, right? But when you divide, be sure that you remember you have another enemy to conquer later, right? Because if you divide by something, that means that there's another case that maybe you have to think about. But don't be afraid to divide. But just remember that you're making work for yourself when you do. But anyway, when I work through the algebra here, I get y is plus or minus 1, x is plus or minus 2, and z is that. So I get these points on the ellipsoid where we're maximized. Well, actually, I get 8 points, right? So you think about all the different sign choices. You got plus, 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 minus, plus, minus, plus, plus, minus, minus, plus, 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 minus, plus, minus, 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 plus, minus, and minus, minus, minus. And, okay, so as you can see, maximum, 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 minimum, 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 minimum. This is that analog to the closed set test I was talking about at the beginning, right? Lagrange multipliers gives you this finite list of possible extreme value points, and you have to just look at them all and choose the winner and the loser. But the whole game is a fraud if your constraint function is not compact, right? If the constraint function is not compact, then you got to use common sense, the setup of the problem, to guide your interpretation. Here's a picture of this one I just did. So the constraint is the ellipsoid, and these are some of the level surfaces of the xyz function. The xyz function is sort of like a two-dimensional reciprocal function. it's got these leaves that open up in opposite quadrants like that. These are the either positive or negative leaves. I think these are the, I forget which ones are which, but one of these is the positive leaves, these are the negative leaves. So anyway, of course, if x, y, and z are positive, it's going to, x, y, z is positive, right? But if one of the three coordinates is negative, then you've got x, y, z is equal to a negative, and those are those. So they give those two kinds of constraint surfaces. Now, it's pretty obvious that you don't want to try to solve these graphically, right? I mean, I don't. I had to work pretty hard to do this, to construct all this picture. And really, all of the work was done with algebra up here already, right? So it's just for illustrative purposes. Here's another find the closest point on the plane problem. We've already seen one of those. Here's a picture of it. Yay. Here's a more interesting one. You'll forgive me if I don't write these out, because if I do, we'll do two examples, and you won't get the big idea, right? We'll write them out tomorrow again, but here's one. A rectangular box without a lid is made from 12 square feet of cardboard, all right? Find the maximum volume of such a box, all right? So basically, the volume, if we let x, y, and z be the lengths of the sides of the box, then the volume is x, y, z, right? And what's the constraint? Well, the constraint is, so did you guys understand why this is? I need to draw a picture for this one. Lights? Thank you. Sorry. You know, the more modern floors in this building don't have these things called light switches, and it's so much less fun. You know, like they have to go up here and press the button. It's like so much more fun to just tell a student the light switch. I enjoy it. It's like one of the best parts of my day. Let's see here. So, and I can't do that in the fourth floor. So I don't know. So I need to label these. Suppose that this is x, this is y, this is z, just for the sake of discussion. We're told that it's a box without a lid, right? So you've got this one xy down here, right? And that's why it's different. There's no xy upstairs. But there is, of course, this one here, which is what? Xz. And this one back over here, which is xz again, right? And then there's the back and the front. That's 2yz, right? So there you go. That's the area of the box, is that. And we're stuck with that being what? 12. So we're forced to use 12 square feet, I guess. So then, Lagrange multipliers, right? I mean, for physical reasons, it seems reasonable that this question should have an answer, right? So, I mean, yeah, this doesn't look to me to be a compact thing. I think this is not a, I mean, I'm not sure if this is compact or not. I don't know. But I'm not too concerned because, after all, x, y, and z have to be, well, I don't know. I mean, x, y, and z have to be non-negative to make sense of this, right? So it may well be that if you constrain yourself to the first octant, that this is actually a compact subset. I don't know. And it doesn't really matter. You just have to be aware of the issue is the thing, right? So here it is, the gradient of, what is this? This is the gradient of our objective function, the xyz function, is lambda times the gradient of the constraint, the area equation, right? And that gives me this equals this, which gives me, and so sometimes I have something like this. It just says to me, you know, I mean, so you just want to make them look like each other, right? So the natural thing for me to do is to multiply that by x, multiply this by y, multiply that by z. Now, admittedly, that assumes something. That assumes that x, y, and z are non-zero. But I already know that x, y, and z are non-zero from physical considerations here, right? So there's no loss in generality in doing that, right? And so anyway, it gives me xyz, xyz, xyz equals. And so then at this point, you can cancel the lambdas, and you just get equations like this is equal to that, right? Which gives me that zx is equal to zy, and this equal to that gives me, see let's see here, the two yz's cancel here, right? And that gives me that xy is equal to 2xz. At which point you can take these and plug them back into the area equation, and it will just give you that y equals x and that, and then you go back to the area equation. 12 equals is this, but I learned that y is equal to x and that y is equal to 2z. So let's see here, what am I going to keep? I guess I'll keep my z. 4z squared, 12z squared. So 12z squared is equal to 12, which means z is equal to 1. And then once I know that z is equal to 1, that makes y equals to 2 and x equal to 2. So again, Thomas would not be surprised that the answer is a square base, because everything else being equal, there's no symmetry. There's nothing distinguishing the length and the width here, right? So the answer has to be a square by symmetry, right? Now, this is why it's important that if I ask an easy question on the test, I use the words like use calculus, because I'm happy that you know about the symmetry solution, but I'm actually looking for you to illustrate to me that you understand the method of Lagrange multipliers and how to execute it, right? And so sometimes I might ask an easy question on the test, because the other thing I would have to do is what? Spoil the symmetry. When you spoil the symmetry of a problem, what happens? The algebra gets much, much worse. Now, I have tried to protect you from that this semester. I could show you what happened last time I taught this course. I could show you things. Here, let me show you something that happened last time I taught this course. Now, I want to show you it. You need to see what you didn't have to do this semester. It's important, because I care about you guys, and I tried to save you time. And I've tried very hard to not assign you certain problems which are very, very, very time intensive. And so let me show you, because I thought I was asking a reasonable question like 2 years ago when I did this. But you know, oh, don't look at that. Oh. I be careful. You're going to see answers to your questions. Here. Oops. Where was it? Yeah, I know, right? Oh, wait, what? Oh, what? Oh, see, now I'm going to have to edit this out. Let's see here. Dang it. Where'd that stupid thing go to? Oh, it wasn't even in this one. Ah. Curses. Where'd that thing go to? Oh, anyway, I'll just tell you what. I assigned this problem. It seems so simple. I had an ellipsoid, all right? Like x squared plus 2y squared plus 3z squared or something. And I said, find the point on the ellipsoid which is closest to the point ABC. I thought it wouldn't be that bad. I found out it's an open problem, more or less. It makes you have to solve a 6th order polynomial when you work out. It's 6th order algebra once you get down to the nuts and bolts of it. And I mean, I started searching the stack exchange, and I found specific ones had been solved. But if I replaced the ABC with like a specific number, like 4, 5, 7 or something, even those kind of problems are like a couple pages and have to have a fortunate quirk between the numbers to make it. So I've tried to shield you from that. I think the problems I've assigned you are not too bad. Shut up. See, now I gotta edit this out now. You hit it? Ian, did you turn it off?